All right, so the goal today is to uh, discuss improper integrals, the last topic in chapter 7. Again, just a reminder, the unit 1 exam on chapter 6 and 7 is this coming week, the 19th. It'll be available on Monday the 19th at 9 a.m. through that Sunday of that week at 11:59 p.m. As I mentioned several times now, don't wait until the last minute to take the exam. Give yourself, several days buffered. That way, just in case anything goes wrong, you have plenty of margin, plenty of time to get it worked out. Because it's open for a full week, there are no due date extensions. And as I mentioned, the Examity practice exam and the Unit 1 exam are now posted. So they'll be available for you to practice the Examity process if you haven't already, and to get an idea of what's on the exam, the length of the exam, the difficulty of the material, and so on. I also, yesterday or the day before, I can't remember now, but I posted 3 short supplemental videos, one on partial fractions, one on approximate integration, and one going through kind of a summary of that integration techniques review worksheet. So we went through 4 of those problems in pretty good detail in class. And I think there were 21 problems, something like that on it. So that supplement goes through the rest of those problems. And, I don't work through all of the problems because that would just be, very tedious and kind of boring. But I think get to the crux of the problem and show you how to get through that. And then, once it becomes just integrating a polynomial or something, leave it there. So any questions on any of that coming up, the exam, anything like that? The rules and so on for the exam are posted on Examity, but basically you can use a standard size 8.5 by 11 sheet of paper front and back with notes, formulas, whatever you would like to write on it. You can use scratch paper, pen, pencil. You can use a calculator, but your calculator has to only be a calculator. So no phones are allowed to be used on the exam, no like tablets or apps as calculators. And the exam will be taken through WebAssign using Examity as the proctoring system. So that gives the flexibility for, days and times that you can take the exam. Okay, the quote of the day today. Sometimes the quotes of the day don't exactly tie into the material for a certain class. This is more geared toward another class where we're talking about things like money and interest rates and things like that. But so just a little short thought for today is fiat currency, or basically money that doesn't have inherent tangible value. So things like dollar bills, or like, some electrons in some hard drive on some server somewhere. Why are we willing to do real effort and work to get these things, these little slips of paper, or these rearrangement of some of these electrons on a bank's computer somewhere? Well, really what that represents is evidence of past productive utility that we've provided to the market that entitles us to productive utility from the market in the future. So this idea of exchanging value for value was a previous quote of the day. This ties into that. I think a lot of times we focus on this last half, right? That if you say, what's money? Well, it's something that gets me stuff, or that's something that gets me services. And I think a lot of times we forget about this first half. And so if you're, taking an economics class, anything like that, I think this is maybe a better approach to thinking about what money is, exchanging value for value, not trying to get something for free. A lot of times that's, somebody promising you something for free is a path to losing all of your money, or a lot of it. And then I like this quote from my mother-in-law that my wife Jen still thinks about to this day, that money is a negotiable representation of your father's time. She would tell her this when she was a kid, and she's like, oh, I want this thing or whatever, and she's like, well, that costs that amount of money. That's that amount of time that your dad will have to work for that. There's an exchange of value for value here. There's no money tree, so to speak. So So that's the idea for today. So moving on to improper integrals, the last topic in chapter 7. So consider the following integrals. We have integral of 2 to the minus x dx, integral of x e to the x squared dx, integral of 1 over root x dx. But really the interesting thing about these integrals is the bounds of integration for the 2 to the minus x integral or the x e to the x squared integral. We see that our domain of integration, the interval of the x-axis over which we're integrating, is infinitely long. It's maybe the infinite interval 1 to infinity or the doubly infinite interval negative infinity to infinity. So if I think about what this might look like as a picture, I know this integral represents the signed area under the curve, but I have an infinitely long area that I'm trying to deal with. Similar thing with this second integral here. The third integral might not look all that fancy. I mean, integral 0 to 1, that's a bounded interval on the x-axis. But 1 over root x, I mean, that's going to look more or less like 1 over x. It has this asymptote going up the y-axis. So this area is going to have kind of a region of kind of height that's going off to infinity. So this is like, in a sense, infinitely tall. So what do we think about these? Well, our first, gut feeling might be, oh, infinitely long area, infinitely tall area. I mean, the area is infinity. There's nothing interesting to do here. Let's think about this for a second, though. So let me come over here and consider something that that's going to be somewhat related, but not exactly this integral. Say we have a circle. Say we have a pie, apple pie or something like that we're serving. And we have a whole bunch of people to serve. So we say, okay, each person that comes up, just take half of what's left. So we have enough for everybody. Everybody gets at least a little bit. So this is, of course, one whole pie. First person gets half the pie. The next person gets half of what's left, or half of 1/2, which is 1/4. The next person, half of what's left, 1/8, 1/16, 1/32. Or if I was to draw this graphically, I might think of making a block of, let's say, width 1 between 1 and 2, and height 1/2. Since this block has width 1, its area is just the numerical value is the same as the height. That area is 1/2. The next block, area 1/4, 1/8, 1/16, 1/32, and so on. We can see that this feels a lot like the integral we're trying to compute. In other words, if we had just thought, throw out my hands and give up on this integral, it's going to be infinity. It's going to be an infinite area. We would expect the same of this, but we clearly see that this just sums to 1. The total area is 1, not infinity. So there's definitely some nuance here. There's definitely some As soon as we start throwing infinities around, right, things get a little more complicated, and we just have to be careful. Now, an integral like this, integral of x e to the x squared, on the positive side, so this is an odd function, but on the positive side, e to the x looks like this. E to the x squared is going to grow faster, and x e to the x squared is going to grow faster than that. So, I mean, it's going to look something like this, and then something like this, right? The factor of x, whenever x is 0, pulls us down to the origin here. And here we're going to be adding up areas that, well, on the right side, the area gets bigger and bigger as we go to the right, instead of getting smaller and smaller as we go to the right. It seems like it's not so great. And I think we would agree that if we had integral 0 to infinity, this actually would be an infinite area, because we go infinitely far in the right direction. It's infinitely long, but it's also infinitely tall. The further we go to the right, the taller the area is, the larger the areas of the Riemann boxes, so to speak, are. But maybe we're tempted to say, well, but this is signed area, this is positive. This would come in negative. So I have something like an infinity minus infinity. Well, infinity minus infinity, that's an indeterminate form. If we remember back to Calc 1 with limits and things like that, we saw things like this come up, and I'm really not sure what to do with this. Should this just be 0? Should it be something else? I don't know. And something like this, if I just swapped x and y, I see that qualitatively speaking, not the exact same function, but if I swapped x and y, or in other words, if I rotated this thing about the line y equals x, I am pretty much back up here at my original question, where I have an infinitely long tail to the right instead of an infinitely tall region. And it seems like maybe that can sum to a reasonable number. So these are the motivations for improper integrals. If I have areas that are infinite in nature, in some sense, infinitely long, infinitely tall, something like that, how do I deal with those? If my domain of integration is an infinite interval, or if my integrand is unbounded on that domain, how do I deal with these types of integrals? Now, something very important about these, like I said, there's a lot of nuance when we start throwing around these infinities. There's a lot of, I'm trying to think of the right word here, but care just has to be taken to follow definitions very carefully and very precisely. Kind of our gut feelings of things quite often fail us in these scenarios. So we just have to take a lot of care. We have to follow definitions very carefully and precisely. And I think there's also an important point that when we write a definition, we say, this is what we mean by this. That's an assumption. That's a statement of fact. And that gives rise to a certain structure, a certain mathematical structure. And, we would probably like most of the time to devise definitions that give rise to structures that are somehow meaningful or useful in the world, or, right? We don't have to. I mean, we could make a definition that's, that's silly, but maybe if it's, as long as it's consistent with everything else we've talked about, maybe it's not that big of a deal. But if people don't find it particularly useful, is that likely to, in some sense, kind of pass through the natural selection of ideas? Or is that probably just going to flounder and nobody's really interested in that topic? So there's a sense in which we like to come up with definitions that are kind of sensible. But when we lay out a definition, we say, this is the definition and that's how it is. That gives rise to a certain structure. Now, there might be some people that look at that structure and they say, well, for my purposes, that structure doesn't really help me very much. So I would like to operate with a different definition and come up with a slightly different structure. Uh, and things like improper integrals, or even more so really in infinite series, which are closely related to these improper integrals. That's the topic in chapter 11. Different people use, particularly in different fields, sometimes use different definitions. So if you're poking around in the internet, you might see some things where somebody says that, this thing that we talked about in class, maybe we said, oh, the integral does not converge or something, and they come up with a convergence to a certain number. So you should always, you shouldn't just take everything in class on faith, but you should ask yourself, okay, there's a discrepancy there. Where's the disagreement? And oftentimes the disagreement is in the definitions that we're using. And oftentimes, if you see things on YouTube or something like that, where somebody is working through some problem and gets some surprising result and gets 4 million views, or maybe in a math video, maybe 40,000 views is a really good result. I don't know. But, if they're going through that, are they really going to be very carefully laying out all of their definitions? So if you see something that seems not to mesh with what we do in class, particularly in things like these improper integrals, or especially in series later on, again, which is closely tied to these ideas that we'll talk about now, ask yourself, are the operations that they're doing consistent with our definitions? That's not to say that our definition is right and theirs is wrong, but if we're using two different definitions, we're really just talking about two different things, right? The same way that a certain arrangement of Roman letters in an American textbook and a similar arrangement of Roman letters in a Spanish textbook, the American might look at the Spanish textbook and say, oh, it doesn't make any sense. But that's just because we're operating on different assumptions, right? Different vocabularies, different grammars, and so on, even though they're the same letters. So there's something a little bit like that here. I just wanted to point that out because a lot of times students in Calc 2 get really confused when they look for external sources, particularly in this section, or with series even more so. And when we're throwing around these infinities like this, we have to be very, very careful about the definitions. A little change to a definition can change the result. Okay, so with that out of the way, that huge caveat, we have our definition. Convergence of an improper integral, and in particular, one of the type with an infinite domain of integration. In other words, the quote, infinitely long or infinitely wide types of areas. So things like this, kind of in a sense. I mean, this also is kind of infinitely tall. So we have a definition. We're interested in knowing what integral a to infinity f of x dx means for some choice of a and f. So we say the following: if integral from a to t f of x dx exists for all t bigger than or equal to a, so integral from 1 to 2, integral from 1 to 3, 1 to 10, 1 to 1,000, 1 to 1,000,000, all of those exist for this particular function, if say a was 1, then we define this integral a to infinity f of x dx, as the limit of integral a to t f of x dx as t goes to infinity. So what we would do procedurally is we would compute integral a to t f of x dx. This would give us the variable x goes away, right? That integrated out, but that gives us a new variable t for that upper bound. So this is going to be a function, let me call it maybe g of t. And then I'm going to limit g of t as t goes to infinity. Okay. And this is, of course, only if the limit exists and is fine. And if the limit on the right side here doesn't exist, or if it exists but it's infinity or minus infinity, then that's not a good result to use for this integral. We have a similar result for infinitely long to the left integrals. If we're interested in knowing the value of the integral minus infinity to b f of x dx, then we look at the integral from t to b for t less than or equal to b. If that integral exists for all t is less than or equal to b, and let me actually put parentheses around this at, whoops. Just the appearance there was a little hard to decipher what was going on with the arrow and the minus sign right next to it. So we're interested in knowing something about the integral minus infinity to b f of x dx. And again, we do a similar procedure. We compute the integral from t to b f of x dx. That gives us a function of t. And then we limit that function as t goes to negative infinity. And of course, this integral equals that number if that limit exists and is finite, just like before. And then lastly, what if we have a doubly infinite integral, a doubly infinite, interval of integration, integral minus infinity to infinity, f of x dx? Well, we interpret that as, well, we pick a number c that's a real number, and we split it into kind of a left infinite and a right infinite integral. And then we evaluate those both independently. I think A and B kind of, make sense. They kind of have a good feel to them. I think C, though, is one where we just have to be extra careful. It's one where we can really easily just try to apply a rule or a heuristic or a gut feeling and be led astray. So we have to be very careful, especially with C. I mean, really with all of these pieces of the definition, as I mentioned, but especially with C, I think we can be easily led astray. We could say, oh, symmetric function over a symmetric interval. We can simplify things, but we have to be very, very careful when we're dealing with these infinite regions of integration. And then just a little bit of vocabulary. In these above cases where the limits exist and are finite, we call the integral convergent. We say it converges to whatever number ends up on the right side here. Otherwise, we say that the integral is divergent. If the integral is divergent, it doesn't have a well-defined value. So I think it's, somewhat bad form to say something like, if the limit on the right side was, say, infinity, I think it's kind of bad form to say the integral equals infinity. I wouldn't say that, but we would say something like, written out, maybe this integral is divergent, something along those lines, or it's divergent because the limit is infinite, something like that. So note that the integral could be divergent because this limit is infinite, but it also could diverge because the limit just maybe doesn't converge. It could be like some kind of sinusoidal, if we integrated sine of x from 0 to infinity, as we're working our way out, the area is just going to keep going positive down to 0, positive down to 0, positive down to 0. That kind of total area never converges to a number. Okay, let's look at some examples. So our example from before, integral 1 to infinity, 2 to the minus x dx. This looks like part A. So the first thing I need to do is integrate from 1 to t f of x dx, and then limit. So the first thing I'm going to do is say, okay, what's the integral from 1 to t, 2 to the minus x dx? Here I'll integrate 1 to t. 2 is e to the log 2. So this is e to the negative log 2 times x dx. I know that if I integrate this, I'm going to get e to the negative log 2 x. if I were to differentiate this, I get the same thing times the derivative of the top. So I get a negative log 2 out. So I need a negative 1 over log 2. And going from x equals 1 to t. Or let me simplify this again. E to the negative log 2x is 2 to the minus x. Just got a pop-up that says low system resources may affect your audio quality. Try closing some applications to improve performance, but I don't have much open. Is anybody hearing my audio cutting out or anything like that?
Seems
let me
fine.
know. Okay, all right, great. I don't know why it came up with that message. Sometimes Zoom just baffles me. But anyway, all right. So if you do have trouble hearing me for some reason because of this message, let me know, and then I can try to fix whatever. I can close the Excel file that I had open for stats, so maybe that'll help a little bit. Okay, so sorry about that. Random Zoom pop-up. But anyway, so we have negative 1 over log 2, 2 to the minus t minus 1/2. I suppose maybe I guess I'll leave this like this. I could switch the order, but I don't know if that's worth writing a whole other line for. Okay, so integral 1 to t f of x dx equals that thing. Now I need to limit as t goes to infinity. So in a sense, like prospective value for this integral, maybe I'll put an equal sign with a question mark here, because it is possible we try to do this limit and it doesn't converge. So then we wouldn't want to say the integral is equal to this, but provided this works out okay, this is going to be limit t goes to infinity. We're going to plus infinity because we're at the top of the integral. Minus 1 over log 2, 2 to the minus t minus 1/2. And I don't know about you guys, but for me, sometimes I get, there's just so much going on. Sometimes I get like a little turned around and I almost like want to integrate this or something, or so, but we've already done the integration. We've already done kind of really the Calc 2 stuff. And now we're just computing a limit. And I mean, just computing a limit, it's not trivial, but just doing the limit here. Our constant comes out of the limit. Limit of the difference is the difference of the limits. The limit of the constant term is just the constant term. So the only piece that I really have to evaluate here is what's the limit t goes to infinity, 2 to the minus t. Note that this is 1 over 2 to the t. And I think we pretty clearly see that that limit is going to be 0. I suppose if we really wanted to, I was going to say we could L'Hopital, but that doesn't quite work. But I think it's pretty clear to see that this limit is 0. So I have negative is a positive 1 over 2 log 2. This does exist. Not infinite, it's finite. So my limit exists and is finite. And I feel comfortable now getting rid of that question mark because I know now that this is the value of this integral up here. This, in other words, this integral is equal to 1 over 2 log 2. In other words, the signed area under this curve is 1 over 2 log 2. again, under this definition, right? So all based on this definition that we laid out here. Okay, so moving to this next example, integral minus infinity to infinity of 1 over 1 plus x squared dx. Let's draw a picture just to get an idea of what it looks like. We're going in both directions, this time minus infinity to infinity. 1 over 1 plus x squared, you might recognize this as something that looks along the lines of, like, say, a normal distribution in stats, like an e to the minus x squared thing. It has a hump in the middle and goes to 0 as we go away from 0. So at x equals 0, it has height 1. And then as x gets larger, either positive or negative, this is clearly an even function. As x gets larger, positive or negative, the height goes to 0. The height going to 0 as we go far to the left or right is seemingly a pretty promising step for convergence of the integral. Now I have a doubly infinite region of integration here. I need to pick a place to split it. I think 0 would be a good place. So splitting it at 0 seems pretty promising. And let me take just the second one and evaluate it. I'll leave this as an exercise, but we'll just take the second one and evaluate it. So first I want to find integral 0 to t of 1 over 1 plus x squared dx. And I know that this is arctan x from 0 to t. What does arctan look like? It goes through 0, 0 because tangent of 0 is 0, right? Sine 0 over cos 0 is 0. We have a horizontal asymptote at pi over 2. And at negative pi over 2. Right? Arctan is an odd function. So it looks like this. So we have arctan t minus arctan 0, but again, arctan 0 is 0. This is what our integral bounded above by t ends up as. And now to compute the improper integral, this half of the overall improper integral, we limit as t goes to infinity of this, which is just limit t goes to infinity arctan t, which is pi over 2. I think we can intuitively look at this and say, okay, this is an even function over a symmetric interval. I see that the right-hand side converges. I think that probably gives me a pretty strong gut feeling that the left-hand side converges and should be the same area. But I'm still going to put a question mark on there because we haven't technically checked this first bit here. So as an exercise, go through, check that, make sure that's pi over 2 as well. And then once this is done, then we can confirm that this integral, the initial integral does converge and it converges to pi. Questions so far? Now let's look at this example. This is a statement that I think is a very plausible one to make. So let's consider the integral minus infinity to infinity of x cubed dx. So here we have on the right side something that goes like this, and on the left side something that goes like this. So we have a positive area and a negative area. And it seems like these perfectly offset each other. We have symmetry. We're integrating an odd function over a symmetric interval. This should be 0, right? The positive area and the negative area always cancel out. In other words, if I integrated minus 1 to 1 of x cubed dx, that's 0. That does work. If I integrated negative 2 to 2 x cubed dx, that's 0. That does work. In fact, if I integrate negative t to t x cubed dx, and if I were to limit as t goes to infinity, that's just limit t goes to infinity of exactly 0, which is 0. I mean, these are all in blue here. These statements are all true statements. Is this a true statement? Let's check. So again, we need to be so careful because, like, why can't I just do this? Can I just do this? Well, that's not what my definition says. This is what my definition says. It says I need to break it up into two singly infinite intervals, two integrals that have singly infinite intervals, and then evaluate them both independently. So if we were to say try to break it at 0, and let's just look at the left side one. If I want to evaluate this integral, what do I get? I get integral from t to 0 x cubed dx that I have to evaluate first. This is 1/4 x to the 4th from t to 0. Well, this is 0 minus 1/4 t to the 4th. Then I have to limit as t goes to negative infinity, negative 1/4 t to the 4th, which is negative infinity. Does it exist? I mean, I suppose. Is it finite? No, it's not. So this integral, can it be evaluated? Is this integral convergent? No, this integral diverges. Note that if I chose a different breakpoint, the breakpoint that I choose, 0 or -1 or plus 1,000 or whatever, doesn't matter. It's going to converge to the same number under any of them, or it's going to diverge under any of them. It doesn't matter which breakpoint I used. I mean, if you could imagine if I had a different potential breakpoint, 100 or something like that, the interval from 0 to 100, that's not an improper integral. That's just a regular integral. So I'd really only care about like those two tails, right? So I could move my breakpoint from one place to another just by adding or subtracting a non-improper integral. So nothing really, there's nothing really consequential about where I choose my breakpoint. I chose it at 0 because that seemed like a convenient place to make the choice. This integral diverges. I don't even really care about this one now, but we could see that this diverges as well. And so we would not want to say this integral diverges. So why can't I instead make this the definition? I mean, I suppose I could, right? I could make this the definition instead, and then, but I might have some problems with that. In particular, I mean, why did I choose negative t to t? What could I have chosen negative t squared to square root of t? As t goes to infinity, these both go to infinity as well, but I might get a different result, right? So my choice of going from negative t to positive t, I mean, it seems like the simplest choice, but it's really an arbitrary choice. There are lots and lots of functions I could put at the bottom and at the top that when I limit as t goes to infinity, they both go to minus and plus infinity as they need to. So, and often under different choices, I'll get different answers. That's probably not behavior that we want, right? We want nice, well-defined behavior. And we want to avoid kind of arbitrary choices like this. So, that's a little bit of the rationale behind why the definition is the way that it is. Makes things nice and consistent. There's not really this arbitrary nature to it, but we might be tempted to do something like this. And while, I mean, this is a correct statement here, it just doesn't bear on this particular problem, right? I mean, you could ask this question, what is this limit? And you could give an answer, no problem. It just is not informative about the value of this integral, even though it might seem like it should be. So again, I'm really harping on this because as soon as we start throwing around these infinities, we need to be just super careful about definitions. And this really carries through again into series, which is a very challenging chapter, really for this, at least in part for the same reason that we have infinitely long sums. And as soon as we throw on this kind of like infinitely long idea, we just have to be so careful about things, not take any shortcuts, not say, oh, my gut feeling is that I should be able to just do this. It's not going to give me the same result. So let's look at this last example in this topic. For what values of p is this integral convergent? So integral 1 to infinity of 1 over x to the p dx. Now, I think if p is less than 0, if p is a negative number, x to the p is on the bottom. So this would be like, if p was negative 1, this would be like integral 1 to infinity of x dx. Right? Do I think this area is going to be finite? No, I think we can pretty clearly see that this is going to diverge. I am kind of breaking my rule here, but I'll leave this as an exercise for you to verify. P bigger than 0, we have some powers of x kind of left on the bottom, so to speak. So we have like a 1 over x, 1 over x squared, something like that. This seems like the kind of integral that could converge. And then what about p equals 0? Well, that's just like the integral of 1 dx from 1 to infinity. And we can pretty clearly see that from 1 to t, this is going to be area t minus 1. As t goes to infinity, this area goes to infinity. So I think this is probably clear enough to explain why p equals 0 has to diverge. I'll leave p less than 0 as an exercise. But p bigger than 0, is this just going to converge for all p's bigger than 0, for some of them? Let's investigate it. So we're going to restrict our attention to the case p bigger than 0. And try to see what happens. Is this just going to converge for all positive p's, or is there a different criterion? So let's integrate from 1 to t, 1 over x to the p dx, or in other words, x to the minus p. So this becomes x to the minus p plus 1, or x to the 1 minus p. Increment the power by 1 over the new power. This is for p not equal to 1. Maybe we'll check p equals 1 as a special case from x equals 1 to t. So this is t to the 1 minus p minus 1 to the 1 minus p is just minus 1 over 1 minus p. And now if I limit as t goes to, my t is on top, my infinity is on top, so I need t to go to plus infinity. Well, the limit of the quotient is the quotient of limits, so the 1 minus p just comes out. The minus 1 just comes out. And really, I'm interested in, let me just kind of come off to the side here. I'm interested in t to the 1 minus p. The limit of that is t goes to infinity, as the base goes to infinity for a given power. And let me, oh, that jumped a little bit. Let me just call this power k. Here I'm just using k equals 1 minus p. For what kinds of k's will this converge? Well, if my base is getting larger and larger, if k is positive, k is bigger than 0, then I have a larger base to a positive power. This goes to infinity. This limit does not stay finite. If k is less than 0, then I have something like 1 over t squared. As t goes to infinity, my denominator gets bigger and bigger. My numerator just stays at 1. This goes to 0, and we do get convergence. Note that k equals 0 is equivalent to p equals 1, and that's our restricted case here. So k has to be less than 0. In other words, 1 minus p less than 0. In other words, p bigger than 1. So when p is bigger than 1, my limit exists and is finite. And I actually get a little bit more out of here. So I can say when p bigger than 1, integral 1 to infinity of 1 over x to the p dx not only exists, not only converges, but is equal to, remember this bit here goes to 0 in that case, is 1 over p minus 1. When p is less than 1, the integral diverges. Oh. We have one special case when p equals 1. Well, when p equals 1, we have integral 1 to t, 1 over x dx. This is log t minus log 1, but that's 0. And clearly this goes to infinity as t goes to infinity. So p equals 1 diverges. We can see that right away. So p less than or equal to 1 diverges, but p bigger than 1 is where we converge, and we get what we converge to kind of for free as part of the calculation. Any questions so far? Okay, and in the last 10 minutes or so, we'll talk about the case of a discontinuous integrand. So here we're looking for integral a to b f of x dx, but we're thinking of integrating things like this. Oh, there we go. Sometimes the equations don't, the equation editor doesn't work so great in OneNote sometimes. But so we're looking at integrals like this, where we don't have an infinite interval of integration, but where, in this case, near zero, near this one bound of integration, our integrand blows up. So we have an infinitely tall area. We have a case that looks like this one here, right? Qualitatively similar to the cases we've been working with. It's just that the infinite leg or whatever goes up instead of sideways. So our definition is going to look pretty similar. If I'm interested in integral a to b f of x dx, and f is continuous on closed a to open b, with that kind of discontinuity at b, so the problem point here is at b, right? Before the problem point was where the infinity was, but here the problem point is at b. So I do the integral from a to t f of x dx, and I suppose I should say t, keep t in the interval a to b, in the open interval a to b. And then we just limit that result as t goes to b from below. So we basically, we sneak up on the problem point with a limit. That limit is the value of the integral if the limit exists and is finite. If we have the problem point at a, we do a very similar thing. We integrate from t to b, and then take that limit as t goes to a from above. And oh, that should be closed to be there. If f is discontinuous at some point c in the interval closed a to closed b, but it's continuous otherwise, then we break at the point of discontinuity. Here it is important where we break. Before it wasn't really important where we break because the problem points were way out at the ends, the infinities. Here it is important where we break. We break it at the point of discontinuity into two integrals, and then we evaluate each of these integrals like these ones above in a and b. And similar vocabulary, convergent and divergent, depending on whether these limits exist and are finite. So let's evaluate integral 0 to 1 over cube root x dx. And again, the first thing that I want to do, and I think to stay consistent with my previous ones, I want to do this in green. The first thing I want to do is I see my problem point is 0. So I want to integrate, I want to integrate t to 1. 1 over cube root x, that's x to the minus 1/3 power dx. I add 1 to the power. This gives me x to the 2/3. Divide by the new power, 3/2 from t to 1. Or this is 3/2 times 1 minus t to the 2/3. My prospective value for this integral is the limit as t goes to 0 from above, the right-sided limit, of 3/2 times 1 minus t to the 2/3. Well, this is just a power function. I can just plug my 0 in. 1 minus 0 is 1. I get 3/2. So this integral does converge. And it converges to 3/2. And I suppose I can get rid of my question mark here now because I've shown that that does work. Are there any questions on improper integrals? Again, I know I've harped on this, but biggest thing is read the definitions carefully, write them on a piece of paper or something and keep it beside you, and follow them very closely, follow them to the letter. I think that's the biggest thing in a section like this. And this is really good practice also for when we get to series at the end of the course, which has kind of a similar feel to it.